So the idea for assuming that the weight should work at the middle, because if you consider the shape of a lamina, for example, let's say this is a non-uniform lamina, I cannot draw the same lamina everywhere. I could have copied it, but then I wouldn't be able to show you the swing. If the lamina is hanged over here for a certain orientation, assume that, and this is the pin, and here I'm drawing a preferable vertical line for my discussion. This line doesn't mean anything for the time being. If the weight of the object is located on the left over here, let's say if the COG's weight, COG is located here, then the weight should work vertically down like this. This would cause a perpendicular distance of the force with the distance over here. So I could label this distance right over here. I would label this over here. But anyhow, this will produce an anti-clockwise movement. On the other hand, if the COG is located on the right, then the weight should work vertically down over here, and that should produce a clockwise movement. So for any of these two cases where the weight is the COG, center of gravity, is on the left below the supporting point, pivot point, or on the right below the supporting point, the object will have unbalanced movement, anti-clockwise or clockwise. And this will cause the object to oscillate back and forth. So it's gonna rotate a couple of times. Eventually, it will come to a steady position whenever the COG will be placed vertically below the center of gravity. So whenever the non-uniform lamina is perfectly made stationary, or it comes to a stationary state when hanged from a freely moving pivot point, this tells us that the COG should be somewhere under this point. So the weight should be worked vertically along this line. Exactly where the COG we don't know, but we do know the COG lies somewhere on this line. এই আইডিয়াটা বুঝতেছো কিনা?
Yes.
Okay. So that's what we do, and then we simply repeat the whole process one more time for a different point. So what we can do is that we just take the pin. So now that's what we find out. But to make sure that we define the line, we use a plumb line. So plumb line is actually a equipment. It's a very simple thing. A plumb line basically means a line or a string that the plumbers use. The plumbers use a heavy mass attached with a string to find perfect vertical. So a plumb line actually looks like this. Let me just show you so that it would be easier for you to understand. This is what a typical plumb line looks like. For example, yeah, this is actually good for you. So this is a heavy mass. This is a cone mast, so that it shows the exact dead bottom center of the whole object, and it is attached with some string so that we can drop it from any height. And if this plumb line is not moving, then that exact position shows the exact vertical below point from a certain point above. It uses with the idea of Earth's gravitational field. And the beauty of a plumb line is that whenever a plumb line is perfectly stationary, so it means it's not moving left or right, this line over here, this string, represents perfect vertical from any alignment, from any orientation. This line represents perfect vertical. So what we do to draw this alignment line, because we cannot actually draw this line by imagination, that would be not right. So from the face of this, from in front of the non-uniform lamina, from this point we hang a plumb line. Let me draw the plumb line maybe with dark blue. So we hang a plumb line like this. You don't have to really draw such a beautiful plumb line. Plumb lines can be also made by any heavy mass or rock that is not gonna be moving, because we don't have to determine exactly where at the on the base of the stand that is. We just want to have this line orientation. So basically what is happening, if you look at the side view, this is the base of the stand, this thing is the stand, this is the supporting pin, this ash color thing is the non-uniform lamina, and in front of the lamina we're going to hang a plumb line like this. We have to make sure the plumb line does not make physical contact with the lamina, because we would like to have no interference or no friction. At this point, when all of these things are perfectly stationary, we're going to try, I mean, what is recommended for the actual exam, this part you shouldn't write in an exam. In the actual laboratory, we ask the students to pinch the non-uniform bar and the lowest part of the plumb line together with their thumb and the index finger. So we pinch this together so they become close to each other. Then using a ruler, we draw up a line that is perfectly vertical from the supporting pin all the way down like this. So we get a straight line through which we know that the COG should be anywhere on this straight line. So that's finding out one alignment. Then simply we repeat the same process once again for a second point. We repeat the same thing for a second point, so which means that if this is our non-uniform lamina, so let's say we did the first thing over for a hole over here, we're preferably going to do another hole that is somewhere in a position so that the other line that we're going to get should cut the first line at a pretty wide angle. What I'm trying to mean is that position গুলো একটু পরে লাগবে, so we can repeat the same process for a second line. এখন যদি আমরা এই সেম জিনিসটা যদি আমরা সেকেন্ড একটা পয়েন্টের জন্য করি তখন সিচুয়েশনটা কিরকম হবে? Let's say we're going to have the stand over here, we're going to have the vertical stand parts right over here, and then we have the pin right over here, and the non-uniform lamina is currently hanging like this, let's say, and we had the first line that was found for this hole right over here, and that line was apparently looking like this. Let me draw it with red, small thickness. So let's say the first line that looked like this is the line that we got for the first hanging point, and then from the second hanging point, which is right over here, let's say we get another vertical line which looks like this. So these are the two lines we get from the two experiment, and that ultimately tells us that this crossing location, which is right over here, should be the center of gravity of the object. So that's how we can find out the center of gravity of a non-uniform lamina. Now there is a very important information. The choice of these two holes is pretty important. These two holes should be placed in such position so that the lines that we have actually make a large angle between them. They should not be really close to each other so that this kind of cutting happens. I mean, we should not appreciate really close points, or maybe the points can be on the opposite side. For example, one point is level over here, the other point is level over here, but the lines that we get doesn't make that much of a wide angle. I mean, the acute angle is actually pretty small. We should preferably try to avoid that. Why, if you ask? The reason is this. Let me show you one thing. Ideally, lines should not have thicknesses. Lines have no thickness, but any line that we draw with our physical equipment, pencil, pen, whatever, they have some thickness. So because we are limited by the idea of thickness too. So I'm gonna today, what's the problem of, what's the advantage of having this thing, okay, and why are we not appreciating this? Let me show you this thing with a bit oversimplified example. Let's say if we have two lines which has thicknesses like this and like this, I'm choosing to draw a pretty thick line to show you one specific concept. In this case, we are pretty sure that the crossing point of these two lines is right here. It's very easy to determine. But if we have two straight lines which are quite close to each other, for example, so one is like this and one is like that, choosing the exact crossing point of these two straight lines can prove to be pretty difficult. I mean, because I drew this on a piece of paper, you can see that, well, sir, the part there where they are the thinnest, that should be our choice. But choosing that point, thinnest point, can prove to be pretty difficult. What my understanding is that if I choose for marking, if I choose a very thin line, let's say, because these two lines start to overlap from this location and they end the overlap in this location, a student who is not very careful might choose any point in between this whole region as the crossing point. Is this error possible or not? Think about it. You might think it's not likely, but it is a possible error. Can we agree on that?
Yes, sir.
Yes, sir. Whereas if we have angles which are pretty large, I mean, if the lines are pretty much producing a wide angle between them, in that case, that problem is not happening. So that's why we'll always appreciate the points to be pretty far away from each other, so that the lines we draw are pretty well apart. So this is the idea of center of gravity or center of mass, pretty much where we can consider the whole mass to be considered. Now comes to the idea, the next thing that I would like to discuss is that the idea for stacking. Stacking means, consider a scenario. Let's say we have a hollow cylinder. Acha, hollow cylinder example of pore jai. Again, normal example. Let's say we have a bar. Currently, I'm choosing to draw it horizontally, but it doesn't have to be horizontal. This is a uniform bar. Uniform bar means it has uniform thickness and such. So the ideal center of gravity should be exactly at the midpoint, right over here. Now try to think. If I bring up a piece of metal and acha, before I go for the additional idea of metal, at this point, because this is the center of gravity of this point, I can actually hang this object by tying up a loop of string over this location. And if I just allow to hang it freely, this will be perfectly horizontal. That's the whole idea of center of gravity, ठीक है ना? Or center of mass, that if you hang it from the exact same point, it will be perfectly stationary. Or even if you don't want to consider the example for a string, if you just put your finger underneath this location. So I'm showing your finger to be a circle because I'm assuming that you're just putting it from yourself and away. So if you put it your finger right over here, so that the weight of this bar works downwards and your applied force works vertically upwards to the same point, these two forces cancel out each other. In that case, also the bar can be held horizontal without any problem. Is it possible? I'm not saying it will be possible to do for a pretty long time, but it is possible for us to balance the bar exactly at the midpoint if we place our finger exactly over there. And if we don't move our hand, this balance would remain for a pretty long time. Am I correct?
Yes, sir.
I think so. What if at this point we attach a heavy mass on here like this? So if we attach a heavy mass, a massive object, maybe a metal piece or something like those, if we place it right over here, would you think this same point can work as a balance point? I mean, if we still place our finger over here, what's going to happen? We're going to have a bigger clockwise movement. So in that case, this side is going to go down, this is going to start going up, because this part has become heavier, this part has become lighter. So if we want to find out the new center of mass that happened, that come into existence because we attached a new mass, we have to move our hand a little bit to the right in such a way so that whenever we're going to place, let's say this is the new point, so that whenever we place our finger right over here, we can once again rebalance the beam. Finding out this point essentially tells us that this is the new position for which the exclusive match of this segment of this bar, and the exclusive mass of this segment of this bar are exactly equal. So that আমাদের দুই পাশে যদি equal mass হয়, তাহলে আমাদের দুই পাশের weight equal হবে, দুই পাশের weight equal হলে আমাদের অবজেক্টটা কি হবে? স্টেবল হবে। এটা ঠিক কিনা?
Yes, sir.
ঠিক আছে? তো এটা হচ্ছে একটা আইডিয়া। আমি যদি এখানে আরো ম্যাস অ্যাড করি, আমি এখানে মানে এইটাই হচ্ছে একটা নন ইনফর্ম অবজেক্টের আইডিয়া, that we don't have equal masses on both sides. So if we start to add more mass on the right, our center of mass should slowly start to move closer to that side, which means if we make one side of an object heavier or more massive, naturally the center of mass would be close towards that side. For example, if I try to drop a planet, for example, let's say there is a planet. This planet is not entirely solid. Let's say it has gas pockets. So let's say this is a planet, and let's say inside there is a large gas pocket over here, and there's a large gas pocket over here. Rest of the part is solid. So let's say rest of the part is solid. এখন, let me just drop some points with green. Where would you think the center of mass of the planet should be? Let's say right over here, option A. Right over here, option B. somewhere around here, option C, or somewhere around here, option D. Where do you think could be the center of mass?
So C.
C is the correct response, but do all of you agree that, well, my best guess is C? Why? I mean, explain this, but in your guess, do you guess it to be C? Everyone?
Yes, sir.
Okay, Naima? Yes. Okay. So this is because there are gas pockets over here. So if we just try to observe the objects, we do understand that if I assume a line around this part would have a lower mass and this part would have a heavier mass. So the center of gravity should be more closer to the heavier side or more massive side. That's why it is slightly shifted to the right. Exactly, the geometric center of this outer circle should not be our center of mass point. So that's what happens. So এই যে বললাম যে ম্যাথটাকে এটা করা আছে, এটা হচ্ছে একটা জিনিস। আরেকটা এক্সাম্পল তোমাকে বলি। আরেকটা এক্সাম্পল হচ্ছে এরকম যে মনে করো আরেকটা এক্সাম্পল দেখাই। Let's say there is a horizontal bar that is balanced perfectly at its middle right here, perfectly balanced over at the middle right here. So this is our support point. We bring two unequal masses, which means this one is 20 gram, the other one is 45 gram, for like here. We bring two unequal masses and we're going to place them on the two other sides of this horizontal bar, balance bar, and we're going to achieve equilibrium. Let's say it just so happens that one of the mass is placed right over here, the other mass is placed right over here. This is how it comes to happen. Now, my question to you, between these two things, let's say X and Y, which one is the heavier one? What do you guess? Remember, the masses that we have brought, one is 20 gram, the other one is 45 gram. We have brought them on and placed them on two other side of the bar and achieved equilibrium once again. Which one do you think is the heavier mass? Which one do you think is the lighter mass?
X is the heavier one.
X is the heavier one, and Y should be the lighter one.
Distance is less, so more forces needed to balance it.
Okay, exactly what you said is absolutely correct. Here's the deal. I mean, what you said is okay, but I'm going to add some more sentence to it just to make it more clear to the examiner. Here's how I would attempt to explain it. See if it's okay, or if you want to add something, I'll definitely take your heed. That is, this is the heavier mass, this is a lighter mass. To achieve equilibrium, we need equal moment. Try to understand. Equal weight on both sides in different places doesn't give us balance. Have to understand. Moment is given by what? Force and distance. Both of these factors are equally important. Not one variable is not more important than the other. So if we bring up some new objects, we once again have to reestablish equilibrium of moment, not equilibrium of weight. Important for you to understand. That's why if you place the heavier object right over here, the heavier object working through a small perpendicular distance can give us the same anticlockwise moment as the lighter object, which has a smaller weight, but working at a bigger perpendicular distance, thus producing the same clockwise moment. So this is what is happening over here. They both have to produce equal moment, but because they have different weight, the heavier one has to be placed closer so that it has a smaller distance to work with, and the lighter one has to be placed farther away so that it has more distance to work with, so that ultimately the product of weight and perpendicular distance becomes equal for each of them. That's what is at play. এই জিনিসটা কি ঠিক আছে? বুঝছো কি বলছি?
Yes, sir.
So the product is important. এখন মনে করো, let's say if I push this mass slightly to the right, what's going to happen?
There is going to be a clockwise moment.
the anti-clockwise moment will become slightly smaller. Beautiful. The anti-clockwise moment, I mean, this moment is going to become slightly smaller because the d will become slightly smaller. This will cause the entire bar to experience unbalanced movement. In that case, the anti-clockwise movement will be smaller, clockwise movement will be bigger, which means the whole bar is going to be more affected by the clockwise movement. Basically means the right side will tip down, the left side will tip up. ঠিক কিনা? ঠিক আছে? এই জিনিসটা আমি তোমাদের এতক্ষণ ধরে কেন বলতেছি? মানে the reason I wanted to come to this point is to go back to explain right over here. What I was trying to tell you over in this figure, that the purpose of this adjustment screw. If it so happens that whenever all of these individual sliding masses are at the zero position, which I do over here, and the bar on the left side is slightly below where it should be, it means that the left side is now producing more moment. The moment is more than what it's supposed to be. The moment on the clockwise moment is less and the anti-clockwise moment is more. So we would like to reduce the anti-clockwise moment. How can we do that? By bringing a part of the mass closer to the pivot. So that part of the mass is this adjustable screw. So at this point, if we push the adjustable screw slightly to the right, then that is going to start to produce a bit of a less moment. It has the same weight because the mass is same, g is same, but as it gets closer to the pivot point, it's going to start to produce a less moment. Ultimately, by adjusting this carefully, you can achieve the horizontal equilibrium once again. Possible kina?
Yes, sir.
বুঝছো অ্যাডজাস্টমেন্ট স্ক্রুয়ের কাজটা? মানে অ্যাডজাস্টমেন্ট স্ক্রুটাকে যদি আমি বাইরের দিকে পুল আউট করি, তাহলে আমার অ্যান্টি ক্লকওয়াইজ মুভমেন্ট বেড়ে যাবে বিকজ ইটস গোনা বি ফার্দার অ্যাওয়ে ফ্রম দ্য পিভট পয়েন্ট, দাস প্রোডিউসিং এ বিগার মোমেন্ট। আর অ্যাডজাস্টমেন্ট স্ক্রুটাকে যদি আমি ভেতরের দিকে পুশ করি প্যাচ দিয়ে সেক্ষেত্রে আমাদের ইটস গোনা গেট ক্লোজার টু দ্য পিভট পয়েন্ট, দাস lowering the anti-clockwise moment, thus it can help us balance it. So this is the purpose of the adjustment screw, which can be used for the adjustment of the device. And one other thing that is also pretty important, that one other purpose other than increasing the range of the device, one other very important purpose that these stones actually provide is that they help us to calibrate the device. Calibrate the device means let's say this mass is labeled to be 500 gram exactly. So how can we achieve 500 gram? You can slide one of these big masses to 500 point value. And if you now place this thing right on this object over here, you should achieve perfect equilibrium. Let's say for some device, for some balance, we don't have that. So we have placed a definitely known 500 gram mass over here. We have placed this big slider at the 500 gram mark, but we don't have perfect horizontal alignment. It means we need some adjustment. How do we do that minute adjustment? By moving this adjustment screw. And if you wonder what if some adjustment screw is not good enough to make the whole thing movement, well, in that case we can choose a lighter adjustment screw if needed, or we can hang a bit more weight from this adjustment screw's neck if we need that. I mean, adjusting a beam balance is actually pretty simple. It's all about placing additional weight or removing additional weight. That pretty much does the trick. এই ডিভাইসটার অপারেশনটা পুরোপুরি ক্লিয়ার হয়েছে এখন বলবান?
Yes, sir.
Yes, sir.
বিউটিফুল। ঠিক আছে, 9:22 বাজে। আমি আজকে এখন আর পড়াবো না। আমি নেক্সট ক্লাসে তোমাদের জন্য ওয়ার্কশিট রেডি করে রাখবো, কারণ প্র্যাকটিক্যালি আমার এই পিসিতে আমার ওলভাসের ওয়ার্কশিটগুলো নামানো নাই। সো আমি নেক্সট ক্লাসে মানে হচ্ছে নেক্সট থার্সডেতে না ক্লাস, হ্যাঁ নেক্সট থার্সডেতে ইনশাআল্লাহ আমরা মুভমেন্ট চ্যাপ্টারের কিছু ওয়ার্কশিট প্রবলেম নিয়ে রাখবো। তোমরা যদি এর মধ্যে মুভমেন্ট চ্যাপ্টারের এমসিকিউ প্রবলেমগুলো অ্যাটেম্প করে থাকো স্কুলের প্রবলেমের জন্য বা নিজেদের জন্য বা হচ্ছে for anything, we will pick up those problems discussion in the next class as well. We're going to first attempt the MCQ paper and then we're going to go for the paper to paper. এখানে ছোট একটা জিনিস আমাদের এখানে বাকি আছে, সেটা হচ্ছে স্টেবিলিটি। ওই যে স্টেবিলিটির কিছু আইডিয়া আছে যে the bigger base more stable, smaller center of height more stable, এগুলো কেন হয়, এই স্টেবিলিটি পার্টটা আমি নেক্সট ক্লাসে একটু করে আলাপ করব, তাই দেন we're going to jump into worksheet solution ইনশাআল্লাহ। ঠিক আছে বলবান?
Yes, sir.
আর তোমাদের আজকের ক্লাসের লেকচার মোমেন্ট লেকচার 2 পার্ট 1 পার্ট 2 পার্ট 3 তিনটা আলাদা ভিডিও সহ আপলোড হবে বিকজ I forgot to pay my subscription to Zoom, so that's why the classes were divided in 3 parts. So it might be a bit troublesome if you want to get back to the lecture, but they'll be well named and they'll be also part of the typical playlist that we operate with. So if you need, just be a bit more careful to see them in sequence, provided you need to find anything out later on. Thank you very much. Assalamu alaikum.